Hello and welcome back. In the previous video, we discussed the potential, and the potential describes how the potential energy of a system will change when a charged particle is added to this system. And just like the electric field, the potential is a property of the system of particles. It's a property of the environment. And when we talked about the electric field, we talked about something called electric field lines, which gave us a way of visualizing the electric field that's created by a system of charges. And in this video, I want to introduce a similar concept for voltage. It's called equipotential lines. And basically, what equipotential lines show is they show paths where the voltage is being held constant. Now, if we go back to the analogy that we can treat positive charges as being like a hill or a high place in a map, and we can treat negative charges as being like low points in the map, and we can treat the electric field lines, remember, as being sort of like the path that water might flow and going from one point to the other. The equipotential lines are very much like contour lines on this map, so they show paths where the elevation is being held constant. Now let's go ahead and look at a very simple example of a point charge. We know that the voltage of a point charge is given by the formula kQ divided by R. So this means that the voltage will be held constant whenever we remain a constant distance away from a point charge. So over here I have these red dashed lines representing the equipotentials for this charge, and we can see that the equipotentials are just circles that are centered on the charge. And this is because every point on the circle is the same distance away from the charge. Now, one important thing to understand is that the equipotential lines are very closely related to the electric field lines. Remember that we can describe the difference in the voltage between 2 points in terms of the electric field, as the voltage difference is equal to the component of the electric field that is parallel to a displacement times the displacement. And what this tells us is it tells us that the voltage will only change when there is a component of our displacement that's parallel to the electric field. So in other words, if I have an electric field that, let's say, points like this, so here's the electric field, if I move in a path that goes like this, so I'm moving perpendicular to the electric field, the voltage is going to be held constant because there is no component of the displacement. Here's my displacement. There's no component of the displacement that is parallel to the electric field. However, if I moved in a path like this, my voltage is going to change very quickly because I'm moving in the same direction as the electric field. So what this tells us is it tells us that these equipotential lines are always going to be perpendicular to the electric field, because if we move perpendicular to the electric field, there will be no component of the electric field that will be parallel to our displacement. And so that's really the trick to drawing equipotential lines, is that you draw paths or curves that are always perpendicular to your electric field lines. So let me go ahead and show an example. And so the idea is that because the equipotential lines are always perpendicular to the electric field lines, the first step that we want to take is we want to draw the electric field lines. So if I have a positive charge over here on the left and this negative charge on the right, remember that the electric field lines always point from the positive charge to the negative charge. So my electric field lines are probably going to look a little bit something like this. So let me go ahead and draw these electric field lines. And the equipotential lines are perpendicular to these electric field lines. So for example, down the center here, all of these electric field lines are horizontal. So my equipotential line is just going to be a vertical line, so it's always perpendicular to the electric field. Now if I move over to the side, like over here, now my equipotential has to be curved, so that when I hit this line, I'm perpendicular to this electric field line. So here I'm going to hit it perpendicular like that, and then my equipotential line has to curve in a little bit so that when I hit this electric field line, I'm perpendicular to this as well. And so this is something that you're going to need to be able to do in this class, is just be able to sketch these equipotential lines. And they don't have to be perfect, but you do have to get that idea that these equipotential lines have to hit the electric field lines at a perpendicular angle like this. So you can see I'm not doing the best job here. It's a little bit challenging to do, but this is one of those things that is very good because it helps you visualize how the voltage is changing between different points. So let's go ahead and look at an example. This example says, use the equipotential lines shown in the figure below to estimate the magnitude and direction of the electric field. So remember that the electric field is always perpendicular to the equipotential lines. So here we have a metal plate that's being held at a constant voltage of 515 volts. And then we have this equipotential line, which is also vertically oriented. It's at 505 volts. And then we have another plate that's being held at a constant voltage at 495 volts. Now, because all of these surfaces, which are at a constant voltage, are vertically oriented, our electric field lines have to be horizontal, because our electric field has to be perpendicular to the equipotential lines. And remember when we talked about the relationship between force and voltage, we said that a positively charged particle would always move from a point where the voltage is high to a point where the voltage is low. And what this means is that the electric field lines point from a high voltage surface to a low voltage surface. So our electric field lines would look something like this. Now, to calculate the magnitude of the electric field, we have to use the relationship between voltage and electric field. So remember that the voltage difference between 2 points is equal to the component of the electric field that is parallel to the displacement times the displacement. Now, we know our electric field lines just point horizontally, like this. So if I consider a displacement going from this plate to this equipotential line, just parallel to the electric field, then we can calculate the magnitude of the electric field very easily. So if I rearrange this, I can see that the electric field is just going to equal the difference in the voltage divided by the displacement. Actually, I need to be a little bit careful about this. The difference in the voltage is minus the component of the electric field that's parallel to the displacement times the displacement. Now you can see here my displacement is parallel to the electric field, so we can just replace this with the magnitude of the electric field, but I do need to keep that minus sign in there. So the difference in voltage when I go from here to here, well, it's going to be my final voltage, which is 505 volts, minus my initial voltage, which is 515 volts. We have this negative sign here, and we're going to divide that by the distance that I've traveled, which is 6 times 10 to the minus 3 meters. And so we can see this negative sign is very important because it's going to make this number in the numerator positive. So if I calculate this, so this is the magnitude of my electric field, I get the number of 1.7 times 10 to the third newtons per coulomb. So that's the strength of the electric field between these two plates. So let's go ahead and look at one more example. This example says an electric field has a magnitude of 4 times 10 to the third newtons per coulomb and is directed downwards. The potential at a point P is equal to 155 volts. The question asks us to find the voltage at 6 times 10 to the minus 3 meters above this point P. So again, let me kind of just draw a little picture of what we have. So the electric field lines are pointing vertically downwards like this. So this is the electric field. And we're trying to find the voltage at a point, so let's call this point P, and this is 155 volts. We're trying to find the voltage at another point up here, and this is 6 times 10 to the minus 3 meters above this point P. So maybe I'll call this F for our final point. So remember that the voltage is related to the electric field by this formula here. The difference in voltage is equal to the component of the electric field that is parallel to the displacement times the displacement. In this case, my displacement is this vertical arrow right here, because I'm moving up 6 times 10 to the minus 3 meters from this point P. Actually, again, I need to be careful. There's a minus sign here. Now, notice that my displacement is in the opposite direction as the electric field. So my electric field's pointing down and my displacement points up. So the component of the electric field that's parallel to the displacement is actually going to be minus the magnitude of the electric field. So it's going to be minus 4 times 10 to the third newtons per coulomb. It's minus because the electric field is in the opposite direction as a displacement, right? And we're talking about the component of the electric field that's parallel to the displacement. So when they're in opposite directions, that number will be a negative number. The displacement is obviously just that 6 times 10 to the minus 3 meters. And so if I plug all this into a calculator, I see that the voltage difference is equal to 24 volts. So my voltage is increased by 24 volts, which means that the final voltage is equal to 155 volts plus 24 volts, or 179 volts. So let's go ahead and look at another one. This question asks, what would the voltage be if I moved 6 times 10 to the minus 3 meters below this point P? So again, my electric field lines are pointing vertically down. We have this point P, which is at 155 volts. And now we're going to move downwards to this final point. And so this distance here, again, is still 6 times 10 to the minus 3 meters. Remember that the voltage is related to the electric field by this formula here. The difference in voltage is equal to the component of the electric field that's parallel to the displacement times the displacement. Once again, I forgot the negative sign. So in this case, my displacement is parallel to the electric field, so my voltage is going to decrease. Now, because none of these numbers really changed, this voltage difference is still going to be the same. It's just going to be negative now, so it'll be minus 24 volts. And this means that my final voltage will be 155 volts minus the 24 volts, so it'll be 143 volts. So one way to think about this, I keep forgetting the negative sign, but if you have a hard time remembering that that's there, think that if I put a positive charge here, it's going to be accelerated in this direction. The electric field will exert a force on it and push it in this direction. And as that happens, the kinetic energy of that particle will increase. So what we would say is that the electrostatic potential energy of the particle is being converted into kinetic energy as the particle moves down. So the potential energy is decreasing, and therefore the voltage is decreasing as the particle moves down. That's why the difference in voltage in this case was negative 24 volts. In this case, we're moving in the opposite direction, so the difference in voltage was a positive number. So the next example asks us to find the voltage if we were moved to the left of point P. So again, our electric field lines are pointing vertically down. We have this point P, which is at 155 volts. And now we're going to move to the left. Actually, let me rewrite that. So we're going to move over like this. This is our displacement. So notice that in this example, the displacement vector is perpendicular to the electric field lines, right? My displacement points to the left, and the electric field lines are pointing vertically downwards. So the difference in voltage, remember, is equal to the component of the electric field that's parallel to the displacement times the displacement. But because my displacement is perpendicular to the electric field, this is going to be 0. So the difference in the voltage between this point over there and this final point is going to be 0 volts. So my final voltage is just 155 volts. And this was the idea that we were talking about earlier in the video, that when you move perpendicular to the electric field line, the voltage remains the same. And that's what we're doing here. We're moving perpendicular to the electric field line. Now, one last thing I want to talk about in this video is what happens to the voltage inside a conductor. Now, remember that the magnitude of the electric field is equal to 0 everywhere inside a conductor. And we know that the voltage difference between 2 points is equal to the component of the electric field that's parallel to the displacement times the displacement. So because the electric field is equal to 0 everywhere inside a conductor, the voltage difference between any 2 points inside a conductor is equal to 0. So this means that the voltage is the same everywhere inside a conductor, because that voltage difference between 2 points in the conductor is 0. So what does this mean? Let me go ahead and just show a little example. So suppose I had a metal conductor, and let's just say that there is some positive charge that's distributed on the outside of this conductor. So I've given the conductor some excess positive charge, and of course positive charges repel, so the positive charge is going to distribute itself on the outside of the conductor. And let's suppose I plot the magnitude of the electric field versus position. So we know that inside the conductor, so from this point to this point, my electric field is going to be 0. And then as soon as I pop outside of this, the electric field is just going to follow the usual formula. So it's just going to follow that formula KQ divided by R squared. But inside here, the electric field is going to be 0. And so we have the same thing on the other side of the conductor. It's just going to kind of fall off like that. Now, the voltage, remember the formula for the voltage for a particle is KQ divided by R. So outside the conductor, it looks like kind of just like a point charge. So I'm going to have this kind of KQ over R type of a curve. However, inside the conductor, the voltage has to be held constant. So I just have a constant voltage in this region right here. So inside the conductor, the voltage is held constant. It's just a horizontal line when I plot it. And then outside of it, it follows that usual KQ over R. So at this point, I think I'm going to end this video. And in the next video, I'm going to talk about the voltage and the energy that's stored inside a capacitor.